Hello everyone, I'm the production director of CRP Robotics, Xiang. I'm very happy to introduce to you how CRP manufactures robots. We conclude that a robot production is divided into 6 major segments: requirements, design, verification, mass production, factory testing, and field applications. In these 6 aspects, we formed a closed-loop system with digital system to drive everything. At the same time, we conclude our production core as this: the requirement is the soul, and decision management is a carrier. Next, I will show these aspects to you in details. First of all, we introduce our requirement part. For the requirement part, we conclude the most important thing is to understand the real needs of each robot's customers. This is what CRP has benefited from years of accumulation. Because of controller current selling quantity has already broken through 10,000 units, through those not selling quantities, we've accumulated a large number of real user experience, and I also know the pain points of our Chinese robots. We have deep understanding of Indian robots' customers. What are their real requirements? At the same time, everyone knows that our China-produced parts such as reducers are the sold with many years development and accumulations. Honestly speaking, although they have made great progress, but compared with global top famous brands, it still has some weak aspects in some respects. So it's very important to us that how to make good use of these reducers and how to good use of them and avoid their shortcomings. Combining the above 2 points, we can build a good robot that is stable, reliable, easy to operate, and used well by customers. Okay, we are now very clear what kind of robots customers need. And next step, we'll introduce our robot design process. We use mature mechanical transmission methods to make good use of Chinese-made parts. At the same time, our mechanical designing core team has more than 80 years of mechanical designing experience. The most valuable thing is they've had design experience in designing RV reducers, harmony reducer, servo and model, so they know the advantages and disadvantages of Chinese parts and components. In addition, we use finite element analysis largely in the design process, especially in the finite element analysis of the limit state. Everyone knows that our robot is a high-speed operation device. It's okay under normal circumstances, but we also need to consider its limit state, especially when designing. So what is the limit state? For example, the robot is in a high-speed operation, suddenly the power is shut down and the robot is suddenly stopped. At this time, the structural parts of the robot, the body, including the reducer, will be greatly impacted. Then for those cases, we'll simulate a similar situation when designing to make sure under this huge impact state, our structure, our body, and its deformation is within the allowable range. We have done 2 typical designs. For example, this picture shows a big arm. We need to make sure its deformation is within the standard range and the peak current of the reducer is within our allowable range. What is the goal of a robot body design? Is that our motors, reducers cannot be damaged for long-term use. And at the same time, our robot body has sufficient rigidity and strength that cannot be deformed for long-term use. Then this can explain why our robot body is heavier. We have done a little research and compared our robot body with other China competitors. Take RH1410 for example. Its weight is 204 kilos and the others are about 170 kilos. For payload of 20 kilos, its weight is about 285 kilos and our competitors are about 225 kilos. Objectively speaking, our mechanical design is also relatively conservative. We need to make sure that our robots still have enough accuracy after being used for 8 years or 10 years. Okay, that's about our design part. Through the above design and simulation process, the good performance and quality of our robot has been theoretically confirmed. So you may have a question. Yes, your design is with sufficient consideration. Then how can you ensure that the data you design is completely accurate? Okay, let me introduce our next step, testing and verification. So for our robot body, we'll have 16 major and 64 minor formal experiments. They are repeated positioning accuracy test, sudden stop impulse test, static torque test, dynamic torque test, robot natural frequency test, motor load rate test, robot noise test, motor vibration test, stress test, etc. And our stress test is very characteristic. We'll attach high-precision stress sheets to all key parts of the robot's small arm, elbow, big arm, waist, and base, and then lead the robot to all kinds of extreme tests and extreme movements. In these extreme tests, we'll always collect the deformation data of the stress piece at high speed and evaluate the actual deformation and the theoretically calculated deformation through the actual data, and make sure the actual deformation is within a normal deformation of the design. Of course, we also do the model temperature rise test. At the same time, when the casting is just cast, we cut it to see the quality inside. Plus, we will do a lot of testings on electronic control system, which is divided into 7 major testings and 43 small testings, including environmental adaptability testing. Simply put, in the hottest weather, the coldest weather, the wettest weather, on the beach, in the desert, it's able to adapt to these environments. At the same time, we also do the vibration test, which simulates our various conditions in various transportation situations, on country roads, sea transportation, air transportation, etc. Make sure a robot can take those conditions without any problem. We also do a variety of electromagnetic compatibility testing. On this type of testing, we'll make a detailed introduction later in this video. We have our network voltage testings. What we simulate in network voltage testing is our real power consumption. We must ensure that our robot can work normally and stably when our network voltage is higher or lower than our rated network voltage, within the scope of our design. And we also need to do some tests on the parameters of servo system and the performance of motion. And there are the motor protection test, motor phase noise test, motor stall test, servo overheat protection test. At the same time, we'll also do some adaptive testing because in the robot adaptation process, we may inevitably use some high interference equipment in the environment. For example, plasma cutting machines, organ welding, they can cause a lot of interference when these devices are installed with our robots. Then we will do some robot adaptability tests here. Here we give some simple test examples. For example, we will do extrastatic discharge test. What's extrastatic discharge test? Here I explain. For example, in the winter, we wear down jackets and at that time we will have static electricity. When we touch some handheld devices, our body will discharge them. For example, when we do teach programming, we will hold the teach pendant, then we will do a test to verify this. Our handheld devices, such as teach pendants, need to withstand this interference when subjected to static electricity. The relevant standards of our country for contact discharge should be 6,000 volts. And when we actually do the test, we will do it based on 10,000 volts. At the same time, we'll also do EFT pulse group test, withstand voltage test, high and low temperature test. Through the large number of testing projects above and the large amount of data collection, we can verify and optimize our design. Well, the robot design is completed and also it passed the verification and testing, and then we entered our production process. First of all, the incoming materials of our production process, the key casting parts, all need to be inspected by the 3 coordinate testing machine, and we use the full inspection method. What is the full inspection method? All the casting parts that are related to the critical precision of our robots, which are related to our robot concentricity, parallelism, and perpendicularity, need to be tested by our 3 coordinate testing machine and other casting testing procedures. In the process of production, our assembly has adopted the process-by-process and streamlined production method. Our assembly uses standardized management, and each step has a work instruction book that reduces the skill requirement for assembly workers. Our assembly line uses a quantifiable process. Let me give you 3 quantifiable examples. As we all know, the 4, 5, 6 axes of robots are conventionally driven by synchronous belts. Then the synchronous belt has a tension force requirement. So what is the proper tension? Instead of using the touch feeling by people, we use a high-precision tensile tester to test whether the tension of our synchronous belt is appropriate. In this way, we quantify our tension. So in our actual assembly process, we can confirm the belt tension is within the allowable range of our design. Second example, for our reducer, we need to add fuel. For the first, second, and third axis, we need to add special RV reducer oil. How much is the oil added? We first calculated through a lot of actual tests. Then we confirm a fuel adding quantity. Then we use a high precision or digital oil adding tanker that we can refine our fuel to grams, such as 150 gram, 240 gram. We will make it accurate to gram. The oil quantity is the most accurate and shareable one. In our working process, the results of the work need to be visualized. So what is working process visualization? For example, there are many screws on our robot body. Many of these screws are very critical screws. Then, in our assembly process, we use torque wrenches for all those screws. What are our working process requirements about this? Every time we see the screw, we will use a marker pen to draw a mark on the screw side. So, this is more conducive to our assembly staff, including the next step assembly staff. They can do a self-inspection and mutual inspection. They can see at a glance whether this screw has been set properly. This process, we call it working visualization of the assembly work results, and of course, we all know that the continuous improvement of this production process is endless. For our production management, how to do it well and fast. This is a never-ending innovation topic. This is our permanent goal. We will continue to improve in many details. Take the 4th, 5th, and 6th axis motors as example. Because the power is relatively small, the conventional method is to use a connector to dock. Although our connectors are already with top quality, but in the actual testing, we found that its reliability still cannot meet our requirements. So how to solve this matter? We have added additional measures to ensure that the connector is in good contact. For the connectors, we will put a friction glue on the back to ensure that the pins will not fall off inside. At the same time, although our connectors are plugged in and there is a special locking device, we feel that it is still not secure enough. So we added an extra pocket and bundled it. Bundle these connectors again, it is guaranteed that it will not fall off in a long-term vibration environment. At the same time, in order to achieve better dust-proof, we also use the plastic bag with a sealing treatment for these connectors. Of course, we will continue to do the work of these details as long as we feel that it is at risk during the testing process or through the customer response. We will find ways to reduce and avoid this risk as much as possible. At the same time, every CRP robot has an ID card. What is the robot ID card? We will prepare 12 forms to record the past and the present data of this robot. What is the data of the 3 coordinate measurement for the key casting component at that time? Who was responsible for the assembly at that time? Who is responsible for the test? Who was the quality control person at the time? If the robot had a problem in the whole production process, who was responsible for solving them? We call it the ID card of the robot. Then imagine that if there is a problem with this robot, We will check the ID card form to further analyze the robot to find out the cause of the failure. And it's a great foundation for us to do the next step optimization on designing and production line assembly management. Let's summarize our production line. Our assembly is standardized, our assembly process is quantifiable, and the result of our assembly are visual. Our assembly process is traceable. Through these methods, we've achieved product consistency. After our products have been produced, then we enter to the factory testing step before sending out. Our factory test before sending out includes 13 automated tests. First, repeated positioning accuracy test. We do the test of repeat positioning accuracy here, which is very distinctive. First of all, we install a rated node block at the 6th axis end of our robot, and also install a rated log block on the 3rd axis of our robot. Then, in this test process, our test has 3 major characteristics. The first characteristic is full trip, which means that when we do this test, each axis of our robot runs from its positive limit to the negative limit. We call it full trip. What's the second one? It's full speed, which means that every axis of a robot has reached its maximum speed during the test. What's the third characteristic? Full load means rated load. With these 3 testing characteristics, we go through the at least 24-hour agent test. And for those testing management, we CRP independently developed a robot automatic testing system. This testing system fully automatically captures key data from our robot in 22 hours, such as repeated positioning accuracy, the current of the model during each movement, in this way to accurately and objectively evaluate the robot. We will also do static torque testing for acceleration and deceleration of each axis. Here I will focus on explaining the significance of the acceleration and deceleration test for each axis. Simply speaking, its meaning is related to the work speed of the robot. Single-axis acceleration and deceleration test. What are our main test objectives? Acceleration, deceleration time, maximum speed, pip current at maximum speed. When our robot is moving at high speed, does it run to the highest speed in enough short time? At the highest speed, is its peak current less than the peak current right now, so that we can evaluate the performance of our robot if it's in line with our design requirements. There is another important test here, the EMC test. What does EMC test mean? We know that there may be a lot of high interference devices on the side of our users, such as manual organ actuating, plasma cutting machine, high and large power inverters. And these devices generate a lot of interference. Then, our test is a simulation of this kind of interference. Our equipment will produce various frequencies, various voltage interference. We add this interference to the encoder feedback line, which is the most susceptible one to interface. Therefore, we can confirm that our robots can also work stably for a long time in this strong interference environment. At the same time, according to the structural characteristics of the robot, we developed a special test instrument. Because everyone knows that the mainstream structure for the 6 axis of operating robots are now hollow structures. Then, once a hollow structure is adopted, it is difficult to use the harmonic transmission method. What is our regular solution for that? Gear transmission. We know the way that gear is driven. If the gear is not processed as assembly wheel, it's easy to create a gap. If there is a large gap, then the repeat positioning accuracy of the robot will be affected. In view of the structural characteristics of this kind of robot, we specially developed a set of 6-axis reverse gap automatic tester. Then it is specially used to test the 6-axis gap, and we will do this test twice. When the 4th, 5th, 6th axis of the robot are fitted into a small arm, we will test the reverse gap of the robot. Then, when our robot completes the 24-hour full node agent test, we will do another 6-axis reverse gap test for it. This confirms the gap between our gears is within our knowable range. According to those large number of professional tests, we can confirm that the performance of our products is outstanding. Of course, we know that we need to know more feedbacks from our clients to constantly improve our robots. On-site applications, customer feedback is very important. So our most important thing is to listen to the voice from our clients. Well, dear friends, let's work together to build the best robot. Thank you all.